So, okay, in my last class, we have already talked about or discussed about one primality testing algorithm. Mostly that was probabilistic primality testing algorithm, and that was Solovay-Strachan primality testing algorithm, which was based on quadratic residues. So, in my previous classes, we have already learned about Legendre symbol, Jacobi symbol, and all. So it was a kind of application of all those previously studied number theoretic problems. So there is another very interesting primality testing algorithm that is known as Miller-Rabin primality testing algorithm, which is again probabilistic in nature. So the algorithm is again ES biased Monte Carlo algorithm that I have already explained in my last class. That is, this is a probabilistic algorithm. That means it will give you the answer, but there will be certain probability that the answer that you get may be a wrong answer. But certainly, if you will be able to bound that error probability, then your algorithm could be considered as a good algorithm. And in my last class, we have already shown that Solovay-Strachan algorithm is such a good algorithm, and it can give you the primality testing with a very large numbers. Say we had in my last class, where I have already shown you maybe 900 digit long prime numbers. It can be checked very easily by using that kind of problem. So that primality testing is very important because we have already shown that in today's scenario, due to the cyber security, the prime numbers play an important role. That's why we need to have bigger primes. So today, according to our syllabus of Presidency University Kolkata, we also have Miller-Rabin primality testing algorithm. So that's why we need to read upon a few things which are the basic things, but I am not going to give you the correctness of the proof. That means the formal proof that will show you why this Miller-Rabin algorithm, primality testing algorithm is correct, the theoretical background. So if anybody is interested to have a look at that, he or she may look at this is the PDF in my book, Basic Modern Algebra with Applications, in the page number 474. So if you go to the 474 page, you will have this Miller-Rabin primality testing algorithm, as well as the theoretical background or the correctness of the proof. But I will, in my class, I will basically show you the basic justification or how it works. That's all. But in our master degree level, the syllabus that we had there, we will have a more detailed proof of that, and that the theoretical aspects of it and why this algorithm is working well or why this has a small error bound, that things we need to prove, and for that we require a few involved calculation using probability and statistics. So that will be required. But for today's course, we don't have those things. I'll just give you the algorithm and the basic intuition how it works. Okay. To start with, let us have some basic idea that we have already discussed in our previous classes. Like if P is an odd prime, it happens with prime, even any prime. If P is a prime, then x square congruent to 1 modulo P has how many solutions? How many solutions it will have? Has exactly
Two solutions.
two solutions, namely 1 and minus 1. So the statement is P is prime. That will imply, so usually we, since we are using for primality testing, certainly we will take as an input as an odd prime. So in that way we can state like this: P odd prime implies x square congruent to 1 mod P as exactly two solutions. Okay, exactly two solutions modulo p. So you can say modulo p. Okay. Now, if I ask you this question, if that is not correct, is the converse true? That means if I ask you the question like this, if I give you x square congruent to 1 modulo n has, okay, so if I consider x square where n may not be prime, for example, if I consider n to be 15, and if I ask you the question, how many solution does this have? Any idea? If n is say 15, which is odd number certainly, but not an odd prime, and if I ask you the question, how many solutions does it have? Any idea how many solutions that you can find? Any any guess? So yes, how many? So you can see that plus minus 1 will certainly be a solution, but the question is there anything else? Well, uh, I can give you a hint. To answer this, you might require Chinese remainder theorem. Okay, okay, let's see what's about if I have this modulo 3 and if I have this simultaneous equation modulo 5. Can you very quickly give me one such solution?
4.
The 4.
So x equal to 4 is a solution, right? Now consider 4 square. How much is that modulo 15?
1, sir.
So 4 is basically a solution here, right? Can you give me another solution very quickly? Very quickly, you should have. You can readily see from here. 4 square congruent to 1 mod 15, from where you can very easily give me another answer.
Sir, 11.
Yes, so that is minus 4, right? So if 4 square equal to congruent to 1, then suddenly minus 4 square is also 1 modulo 15, right? And what is minus 4? This is nothing but 11. So 11 square is also 1 modulo 15. So you can see that uh, we have at least 4 solutions, right? So what are the, so if I consider this 1 modulo 15, then we have already seen that plus minus 1 were a solution and plus minus 4. So the question is there any more or something else? Okay, so we had this equation. Now if I just little bit modify this equation, like if I have x congruent to minus 1 mod 3 and x congruent to 1 mod 5. Can you give me very quick solution for that? So minus 1 means actually 2, right? Can you give me a solution for that?
Sir, 11.
So 11. So x equal to 11 is a solution. Now you can see that x equal to 11 is already there. That means this is nothing but minus 4. So if we consider this sorry, this is if I consider 1 modulo 3 and x congruent to 1 modulo 5, then what will be my solution? If I consider this and by using Chinese remainder theorem, well, what will be your conclusion? X value will be It's very easy.
16.
Modulo 15 means 1, right? So this is 1. So that is also a solution. And another one more set is I left it. So this is -1 modulo 3 and x congruent to -1 modulo 5. Now tell me quickly what will be the solution for this.
So -1.
-1. So that means already there. So you can see that all the things, all the equations that we consider, out of which, so you can have four such set of equations. Like, so I started with this. So this is, you can say, one set where I have just interchange these values. So I have these values, that means x congruent to a mod b mod n. If I consider this one, say n1, and x congruent to b mod n2. So here my n1 and n2 are fixed, they are 3 and 5. Well, now I am just changing these values. So what could be the values? A could be plus minus 1 and b could be plus minus 1. And so out of which, so there are two options for A, there are two options for B. So altogether options for AB, there will be four such options. So I should have four such different equations. So this is one system of equation, this is another system of equation, this is another, and one more should be there somewhere. So this is 1 1 -1 -1. Yeah, so here this is, so 4. So out of this four such system of congruences, we have
Sir,
altogether, yes.
sir, these n1 and n2, they are prime distinct prime numbers, or there can be any co-prime numbers.
No, till now I have just taken two distinct prime numbers
Okay, sir.
for this equation for
Okay, sir.
15.
Yes,
Yes.
sir. So we can
So I,
for any, so for any distinct PQ primes, so we can have the same system of equations. Only four.
exactly, exactly. So if we have n1 and n2 are two distinct prime numbers, then suddenly we will have four square roots, right, of the equation. What we started with, we started with x square congruent to 1 modulo p1 p2. If this is my form, then you can understand very easily that there exist exactly four distinct square roots of this. That means there will be exactly four solutions, and you can see that what could be the solutions in case of 15. Okay, so that means if you can see that if I start with this 1 modulo p, then we had exactly two solutions. But if I have p1 p2, then we could have more solutions, 4. So x square congruent to 1 mod p is the only kind of equations where we could have two solutions, right? So we have already seen, not, we couldn't prove yet that only two solutions, but this statement is at least correct, that if p is an odd prime, you can consider p to be even. I mean, if you consider x square congruent to 1 mod 2, then how many solutions you will have? So here you have exactly 1 square equal to minus 1 square, right? So 1 equal to minus 1 here. That's why it will have exactly one solution, not two solutions. So but if you have odd prime, so I should have here also, I should have its odd prime is an odd prime. Okay, then you, this kind of information is very important for my this primality testing algorithm, which we are going to show now. So until what I explained is correct, is it clear to all of you? Okay, so if so, then let us come to here. Okay, so second observation that we can think of, Like in my last class, we have already shown that if A implies B, if this is the statement, then the logical equivalent of this is negation B implies negation of A. Okay. So here what we are doing is P is odd prime, that implies x square congruent to 1 mod P has exactly two solutions. And the solutions are namely plus minus 1, of course, modulo P. Now, if I just change this in terms of negation of this, that means if x square congruent to 1 mod n or P has more than two solutions, then what will be your conclusion? The conclusion will be P is not an odd prime. So of course we'll take as an input as odd numbers. So that means it may be even number, but since we are including only odd input as odd number, the conclusion will be n must be composite. So what does it mean? So if x square congruent to 1 mod n has more than two solutions where n is odd, what will be your conclusion? The conclusion will be that should imply, or if I drop if, that means if x square congruent to 1 mod n has more than two solutions, n is where n is odd, what will be your conclusion from here? So that is the almost negation of this, the negation of this. That means P is an odd prime. So the negation will be P is an composite because we have already taken. So this negation could be P is not an odd prime, right? Not an odd prime includes two. It could be two. But since we have taken n to be an odd number, the 2 value of 2 is already discarded. That means here the conclusion will be n is composite. Is the argument clear? Is the argument clear to you? If any question or doubt, please let me know. Yes. Is it clear? Okay. So hope that this is clear to you. So that's the basic idea for Miller-Rabin primality testing algorithm. So let us come to here. So I'm not going to the details or the historical background of this. I'm directly coming to a basic idea. Okay. So for an input, what you will basically take here for an input here, we are going to take odd number, right? So the question is whether that odd number is prime or not. So the problem will be here like this. So there will be, what happened? Yeah. So the problem is, so here, this is will be an algorithm. So algorithm will take some input n. So n has to be odd number, and your algorithm will able to say whether the odd number is composite or not. So yesterday we have checked, the question was is composite. So it was a decision problem. In my last class I have already mentioned about. So is composite. So this is my decisional version of the problem. That is, if I give you some input n, and if I ask you the question, is that n a composite number? Then your answer will be either yes or no. So in my last class, we have already shown that this is a Solovay-Strachan algorithm can be used here. and that was a yes biased algorithm, Monte Carlo algorithm. That means if it gives you the answer yes, then certainly with probability 1 the answer is correct. But if the algorithm gives you the answer no, there might be some probability that your answer is wrong. That means you have given some odd composite integer and it should give you the answer yes, but by mistaken it has given you the answer no. But we have already given the result that even if it gives you show, the probability of giving that bad answer, that means a wrong answer, is very less. And we have shown that you can run your program maybe 100 times, that to make sure that your answer is almost correct. That means the probability of error could be half to the power 1 by 100 if you run the algorithm 100 times. So if you are not quite sure that okay, the half to the power 100 is not that accurate for you, then you can think that okay, then you can make it maybe 1,000 times you can run your program, then the probability of error will be half to the power 1,000 and so on. So that is the basic idea, that how you can reduce the error probability. So today I am going to deal with another such problem or another such algorithm, which is again an yes biased Monte Carlo algorithm, which actually gives you the idea how the error bound can be bounded. Okay. So here this idea is we need to check something. So previously we used the idea of Legenders symbol, Jacobi symbol and all, but here also we are using the concept that if x square congruent to 1 mod x square congruent to 1 mod n, if this will have more than two solutions. So we can see that plus minus 1 will always be a solution of this. So plus 1 and then minus 1 will always be a solution. But if you have more solutions than plus minus 1, then your conclusion will be the number is composite. Okay. So that is the basic idea. So let us try to formulate this. So what you are given? So you are given an odd integer n. Since this is an odd integer, so n minus 1 must be even. So n minus 1 must have some even integer. That means it will contain 2 as a factor. So just try to take it out, the maximum 2 portion of it, and say write it like this to say t. Okay. That means suppose I have given you say n to be say 101. Say n is 101. Okay. So this is an odd number. Now I consider n minus 1. This is 100. Now take the maximum even portion from it. That means to square that you can take it out, and then this is 25. Okay. So we can write always an odd number in this way. Okay, where h should be greater than equal to 1, right? So if this is odd number, say which is strictly greater than, say greater than equal to 3, then you can always write in this way. So this 2 to the power h plus t is clear to you. So that means the value of n is nothing but 2 to the power h into t plus 1. Okay. So that's the idea here, where GCD of 2 and t is equal to 1 and h is greater than equal to 1. Okay. What I am going to calculate is a to the power n minus 1 modulo n. I want to calculate. So what we can write it, a to the power n minus 1, a to the power n minus 1. So what is this value? I want to calculate this modulo n. So what is this value? A to the power n minus 1 is nothing but 2 to the power h into t modulo n, right? So that's what I have written it like this. Now you can find this is a to the power t, 2 to the power 2 to the power h. That means you can write like this, a to the power t modulo n 2 to the power h, or you can put a to the power t to the power 2 to the power h modulo n. Okay, so this value, that means a to the power n minus 1, a to the power n minus 1 may be calculated in h plus 1 intermediate steps if we let b0 equal to a to the power t modulo n. That means if we write like a to the power t equal to b0, then what you will do? First you calculate a to the power t, that means b0, then you calculate. So here the 0 means value of h is 0. Then you calculate b1, which is nothing but a to the power t 2 to the power 1. Okay. Then you calculate b2, that is nothing but a to the power t 2 square. So that means starting from 0, you are basically step by step you are calculating b t, that means bt. Okay, that means with t plus 1 steps, sorry, bh, so this is h, the power is h, so you are calculating b0 b1 b2 dot 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 b to the power h, sorry, bh. What does that mean? That means a to the power t 2 to the power n. Okay, that means the whole thing, this is thus a to the power n implies a to the power n minus 1 modulo n may be calculated in h plus 1 intermediate step if we let b0 to be a to the power t, then bi is nothing but just making them square, that's all. So every time you are making square 2 to the power 1, then you are, if you making it again a whole square, then you will get a to the power t 2 to the power 2 square and so on. So every time if you make a square of this, you will finally with h many steps, h plus 1 many step, you will ultimately reach to a to the power n minus 1. Okay, so the idea is like this. Suppose you want to calculate n is here 325, so n minus 1 is nothing but 81 into 2 square. Okay. Now what is your, so this is your t. So suppose you want to calculate a to the power this value, a to the power 325. So here it's your t is 81, so start with a to the power 81 modulo n, so that is your b0 value. Then calculate b1, so that is nothing but making a square of this a to the power 81 whole square, you will get this. Then what is b2? b2 is nothing but again making a whole square of b1 square. b1 square will ultimately give you this value a to the power 324, what you actually wanted to calculate a to the power n minus 1. So you are done basically. So here starting with b0, if you know b0, then if you make a square of 2, that means within 3 steps, say b0 b1 and b2, you will ultimately end up with b to the a to the power 325 minus 1. Okay, so that's the basic idea of this. Okay, so now we'll consider a table. The table is sorry. So now we'll consider a table, and using that table, we'll able to make you understand what is exactly happening here. Let's see where is that table. Okay, let's see. Yeah, so this is the table. Okay, so you want to calculate basically a to the power 324 modulo this for different values of n. Okay, so here a is I have taken the values of a to be this. Well, so it is a, then b0 is a to the power 81 because I want to calculate a to the power 325 minus 1. As I mentioned, this value is nothing but starting with a to the power 81 modulo this. So a to the power modulo this value is 252. Then if I make a square of it, it becomes this. If I make a square of this, this becomes this. Okay. If I consider the value of a to be 307, then I will get this. Note that this value 324 is nothing but -1 in modulo 325. That means if I start with 7, then B0 value will be 307, then B1, that means B0 square is -1, so this value is nothing but -1, and then if I make a square of this, then suddenly this becomes 1. So if you start with 18, then also I will have the similar pattern. So 18 squared is -1, and then this is 1, and so on. So you check with these values. Now the final important observation is like this. So you start with some values B0. Okay. Now what could be the values of B0? There may be different stages. Okay. It could be, you may start with the value of B0 to be 1, then if you make a square of this, then suddenly that becomes always 1. So if you start B0 to be 1, then what is B1? That is B0 square, that will be also 1. And then if you make a B to the BH, then that value is also 1. Okay. So this is one case. You may start with -1 value, that means -1 modulo n. Then if you make a B1, then suddenly square of this becomes 1, and once you get 1, all the remaining values will become 1. Okay. You may start with something else, that means not 1 or -1, something else value, and also of course non-zero. Okay. If you start with this, then it may happen that this is something non-zero, non-1, non-1, but its square becomes 1. But once this square becomes 1, then these values all becomes 1, right? Okay. Now start with this. So this is, start with something not equal to 0, not equal to 1, not equal to -1. But if you start with this, and suppose its square becomes -1, then after all stages that becomes 1, and so on. So this is basically the starting point. After how many steps you will get 1. Now my question is it always 1? It may happen that you start with something and you are going to make one square of each of them, and it will star means that is non-zero, non-1, non-1. It may also happen like this. So when we started with, in my in the previous example, when we started here, yeah, when we started here, you can see that if we start with 252, then this value is not 0, not 1, not -1, and this value is also not 0, not 1, not -1. Okay. So this may also happen here also. So there is one case where you will never achieve 1. You will never achieve 1 in any of this case, or -1. It may also happen that at the end you will end up with -1. Okay, in, let's see if in my previous example whether there is any case. No, here we don't have any such case where we finally end up with -1. But it may happen that you start with somewhere, and something values, when you come up to b to the power h, you come up with -1. Okay. And remaining cases are similar. You start with something, at in between some places you reach to either -1 or 1, and once you reach to minus or 1, you ultimately end up with this 1. Now my observation is, if you reach with somewhere where you start with some star, and at the end you come up with 1, then your conclusion is n is composite. Again I am repeating, you start with some star, and through this calculation, that means h plus 1 steps, you find that you ultimately end up with 1 at the BH step, then your conclusion is n is composite. Can anybody explain why it's so? What is the justification? I have already explained all the justification. Just you have to collect, or you have to connect all the things.
So then it will have a solution other than 1 and minus 1, as x square is 1.
Exactly. And as a result, you will
In
able to tell that, that means if you go back, not in this way, if you go back, so what is this? So bh minus 1 square is nothing but bh. So this is nothing but a square root of this. Okay. So square root of 1, you get only one answer. Square root of 1, you get only. So now go backtrack, just go left hand side. So at this stage, from minus 1, what you will get? You will get a star, or from 1, you will get a star. That means the square root of this has some non-trivial solution, not is not 1 or minus 1. So when that will happen? If n is your a composite number, then only this will happen. As a result, your conclusion will be the number is composite. But if it happens, for example, here you have 1 and then minus 1, and then from here you will get star. So here you will not be able to conclude anything, no information, because I am only considering square root of 1, not minus 1. So at any point of time, if you get minus 1, then after all these steps that becomes 1. But before that, you cannot give any conclusion, because from 1 you should get star just before 1. If you have at any step, if you have star just before 1, your conclusion will be n is composite. But you cannot say anything uh, in other cases. For example, here from 1 you will have minus 1. That is valid, because in case of, so square root of 1 is minus 1, that is also valid. But you cannot ask the question for minus 1, because we are not considering x square congruent to minus 1 modulo n. So our logic is basically for only for x square congruent to 1 modulo n. As a result, you will have the conclusion only when you have 1 here and just before that you have some star here, or there will be another, there will be another place where you can have the similar argument, that is when you have all stars. Why this is so? Can anybody say me why this is so? Why, if at the end, if we don't have one, anything other than 1, then your conclusion will be n is composite? Can anybody be explain why this is so? So what is this h to the power n minus 1, right? So sorry, bh, that means a to the power n minus 1. If that is not equal to 1, then your conclusion, so what may happen? That may be 0. Okay, if that is 0, we cannot say anything. So what I am talking about, either this is minus 1 or star, then your conclusion will be the number is composite. Why this is so? Anybody? Okay, so you need to think a bit. If you calculate with few of these examples, then it will be clear to you why this is so. I'm not giving you the hints, but it's not very difficult. It's easy. So maybe Fermat's little theorem you might use here, or Euler's theorem you might use here to get the answer. Is the question clear to all of you? Or is the algorithm clear to all of you? Is the algorithm clear to all of you?
Yes, sir.
sir, sir,
Yes.
sir, if
Yes.
n is if n is a not a composite number, then by Fermat's theorem it will be 1, because it is
Yes.
a to the power p minus 1.
Yes.
So n has to be composite.
Could you please repeat once again?
The last term will be a to the power n minus 1. So,
Exactly.
and that is not congruent to 1, but if n is a prime number, then
Yes.
a to the power p minus 1 will be congruent to 1 by Fermat's little theorem.
Yes.
So it is not 1, so it cannot be prime.
Yes. So it has to be composite.
Composite.
Clear? So what is this last step? Last step is nothing but, so what is BH? So again, if I write once again, so this is 2 to the power h into t plus 1, right? It was the notation. Is the notation clear, right? Or
Yes, sir.
okay, yes. So yeah, so what is my B0 is nothing but 2 to the power t, right? So what is my BH is nothing but, uh, so this is not B0. I think B0 is a to the power something. So this is B0 is nothing but a to the power, what is B0? Let me check.
A to the power 2 to the power t.
So a to the power,
2 to the power t.
yes. So a to the power 2 to the power t. So I can write it like, so n minus 1 is nothing but 2 to the power t 2 to the power h, right? So so this is my 2 to the power t is, so this is my B0. So what is my b to the power, b to the power bh? This is nothing but a to the power, uh, 2 to the power, so I messed it a little bit. Okay, so just follow the notation of the book, otherwise it will be two types. Okay, yeah, yes. So uh, here B0 is a to the power t modulo n. So B0 is a to the power t. So this is, it should be a to the power t modulo n. So I'll just, so my h is 2 to the power h into t. Yeah, 2 to the power h into t. So n minus 1 is nothing but 2 to the power h into t. So what I want to calculate, a to the power n minus 1 modulo n. That is our m. That means we actually want to calculate a to the power 2 to the power h into t modulo n, right? And so I make it a to the power t 2 to the power h modulo n, right? So I consider this to be my B0, and then every time B1 means B0 square, B2 means B1 square, and so on. So at the end, what you will get? Ultimately, you will end up with B to the power BH. So this is nothing but B to the power BH minus 1 whole square. And if you go back to this, ultimately you will end up with, in terms of B0, you will ultimately, you will end up with B0 to the power, how much? B0 to the power
Right.
H. Okay. So in h plus 1 steps, you will basically achieve this. So if we know that by Fermat's little theorem, if p is a prime, then this value is nothing but,
So will it not be b not to the power 2 to the power h?
yes, b to the power 2 to the power h. Yeah, yes, yeah, it should be b to the power 2 to the power h. Yes. So if so n prime will imply this. That means logically equivalent to, if that does not happen, mod n, what will be your conclusion? That will imply n composite, right? So that is the idea. If a to the power n minus 1 modulo n not equal to 1, then your conclusion is n is composite. So that's why here, when we go here, if at the end, if we have anything other than 1, your conclusion will be n has to be composite. Now it's clear to all of you? Clear? Good. So that is the basic idea of, let me check, I must have some in a box format where we have. So they are the basics. So it's a layer and some technical terms are here to prove this. Miller-Rabin test is a Miller test is a I mean it works properly or perfectly. So to prove that any Miller test, so it's not a Miller, so it's a Miller test. So it's basically to show that it really gives you the correct answer. You need to have some proof, and the proofs are little bit complex, or you can say involved. Not very complex, but it's little bit involved. So if you're interested, you can certainly have a look at this. So I think, yeah. So this is the Miller-Rabin primality testing. It's a very small form. So input is your n, which has to be an odd number greater than equal to 3. So what you are going to do is basically you just write it in terms of this, as I've already mentioned, where h is greater than equal to 1 and GCD of 2 and t equal to 1. That means you have taken out all the even part from this n minus 1, and that becomes 2 to the power h. Okay. Then you have to choose a random integer a whose value is between a and, sorry, 2 and n minus 2. Okay. Now make 2 to the power t. So you have already t at your hand because you have written in terms of n minus 1 in terms of 2 to the power h into t. So you have a, so you have chosen a randomly between 2 and n minus 2. Then you calculate a to the power t. Okay. If b congruent to 1 modulo n, that means if a to the power t equal to 1, then the number is a prime integer. See, if you go back here, if you go back to my slide, yes, here. So that means at the very first step, b0. So this is nothing but a to the power t. So if this value is your 1, then your conclusion is no information. Mind that what we are going to do here, we are going to, the question is composite. So this Miller-Rabin primality testing is, the question is composite. So is composite. So your input is odd n greater than equal to 3, where n is odd, right? And your answer is yes or no. So when you have this conclusion, when you have this conclusion, so the number is composite, what will be your answer in case of is composite? The answer will be yes, right? If you get, because the question was is composite, so when you get the answer that is n is composite, then you should return yes. And since I have told you, you must return some value, yes or no. When you have no information, you should return the number is not composite. Okay. That means you might have some wrong information here. So when you say n is composite, that means you should return yes. When you have no information, then also your algorithm must return something. So what should it return? You cannot say that it also return yes, because yes you have already given when n is composite, because the question that I asked was is composite. So when it says yes, the answer must be correct always. But when you have no information but you have to return some information, then the best thing is that say no. So there might be some wrong answer. Okay. So whenever at starting level, if you have 1, then suddenly all of them will be 1, remaining all the steps will be 1. So you will have no information. That's why the algorithm says that when you have b to the power b is congruent. What is b? B is nothing but a to the power t. So if b is 1, then return no, the number is a prime integer. That means in according to that table you have actually no information. Now you are going to make a square of each terms. So what you are doing, if you have at any step, so you are basically making a square. So this loop actually makes a square. So b square, b cube up to b to bh. Okay. So what it is doing? So that's why from 0 to h minus 1. So the h penny terms it will make it zero, make it a square. But if at any stage if you get b value is minus 1, that means at in my table if you have b value is minus 1, this b value is minus 1 at any step. If you have minus 1, after that what you will get, your answer will be no information except for the step that here at the end if you have minus 1, then only the number is composite. Otherwise in the remaining step, that's why you can see that the loop was from 0 to h minus 1 and not till h. So the loop was till h minus 1. That means at if you have from anywhere in between, if you have minus 1 from here to here, the conclusion will be no information. Wherever you get minus 1, after that all the steps becomes 1 and remaining it will be some star. Because if you have 1 here, you cannot have minus 1 right hand side of that. That means wherever you get minus 1, your answer will be no information. So in my algorithm, what it should give? That it should return that the number is prime. So in between, see, it's up to h minus 1, because if it is at the h level, then the conclusion will be, the answer will be the number is composite. But in between, if you have minus 1 at any place, you will have actually no information. As a result, you should return the number is a prime integer. Okay. Now see, when it will stop, it will ultimately, when the value of h, it goes up to h minus 1. So when it goes up to h minus 1, this when it will do basically when it the value of this is h minus 1. So it's from 0 to h minus 1, it's continuously doing. When it will come out, see, at any point of time if it gives you the value minus 1, then return means, in my last class I have already mentioned, return means the program will terminate here with this value. If it returns, that means if at any point of time this value becomes minus 1, then the program will terminate and give you the answer no, the number is a prime integer. But when it comes out, that means at none of these places this value become 1. That means when it comes out, so, sorry, the value becomes minus 1. When it comes out, that means for the h step, last step, it becomes, it is not minus 1, or uh, it's not minus 1 basically. So as a result, what will be your answer if you go back to the table? Yes, if you go back to the table, at the last step, what was your conclusion? The conclusion will be, if you might have star here, you might have minus 1 here, then your conclusion will be the number is composite, and that is the correct answer. Is it clear? Is it clear to you? The last step. Okay, you just have a look it once again, then it will be quite clear to you. Is it clear?
Yes, sir, it is clear.
Yeah, so it's just the algorithm. We have already started with bit a to the power t. So b0 is already calculated here, right? So it starts with actually the last steps. So 0 to h minus 1 means h. So h many squares it's making actually, and at the end it gives you the answer. If none of them is -1 in between, that means it comes at the end. And when it comes at the end, that means you will either end up with a +1 or -1 or star, and then your conclusion will be the number is a composite integer. Clear? So you need to read a bit about this. So just not the proofs, you just have a look at the theorems. So at the end what it says, that Miller-Rabin primality test is a yes biased Monte Carlo algorithm. This is important. Is a yes, that means when it says yes, the answer is 100% correct. But when it says no, there might be some error probability. And at the end, we have shown that this has the error probability is less than half, like Solovay-Strassen algorithm. So the proof is somewhere, might be here. Let's see. Yeah. So you can see that many probability and statistics are involved here. Yes. And at the end, uh, so this is the error probability actually. What we have proved that it is less than 1/4 actually. So you can say it's also less than half. So you don't need to read all the details about the proofs, but it's sufficient to have the algorithm, just algorithm. So that's there in our syllabus. So that's the Miller-Rabin primality testing algorithm. But if you are interested, you can have a look how it happened actually, how the progress happened. So in this connection, I would like to mention that they are all probabilistic primality testing algorithm, and they are very efficient, because in my last class I have already shown you how efficient are they. My small laptop can find 900 digit long prime very quickly. Maybe it takes maybe 30 seconds or 40 seconds, but still it can compute. So the question is there any deterministic efficient algorithm? Well, you'll be very glad to know that three Indians, uh, one of them is from the Kanpur IIT Computer Science Department, and two of his students, Manindra Agarwal was the professor, and two of his very brilliant students of computer science, Kanpur IIT, Nitin and Neeraj. So three of them, they for the first time showed in the history of mathematics that there exists polynomial time algorithm, that means efficient algorithm, which are deterministic in nature and which can check whether a number is prime or not. That means primality testing algorithm can be done efficiently by using deterministic mechanism, which are polynomial in nature. That means there exist efficient algorithms which can test deterministically whether a number is prime or not, and that is known as AKS algorithm, and that involves mostly ring theoretic techniques, very easy to understand. So if you are interested, you just type with primes in P means uh, polynomial time algorithm, collections of all polynomial time algorithms. So if we just type primes in P, you will find the seminal paper done by these three. One of them is a faculty member, Manindra Agarwal, and two of the students, Nitin and Neeraj. So excellent papers. And after that, you can understand it was a long-standing problem that people had a doubt that whether you can have efficient deterministic algorithm. It was a long-standing problem